record. Okay, welcome everyone to the Simon's Quantum Tuesday seminar. I hope you're all doing well. Thanks for joining. So let me just remind you for questions. So I think when you join, you're muted. Actually, you're not, but I'll do that now. So when you join, you're muted, but you can unmute yourselves and ask a question. So Ronald asked that you please interrupt him and ask questions. If for some reason it's easier for you to type the question in the chat, you can also do that, and I'll see it and I'll interrupt the speaker. But really, you should feel free to just speak directly. All right, okay, so today we're very happy to have Ronald de Wolf from CWI, QuSoft, and University of Amsterdam. And Ronald is going to tell us about work that he started working on with Srinivasan, who I think at the time was his student at PhD student at CWI, and then he attended our quantum cluster 2 summers ago, gave a talk about it, and I think Andrew was there in the talk, maybe Robin was also there. Other people got interested and they continued work, and so Ronald is going to tell us about their achievements on the quantum coupon collector problem. So Ronald, welcome. Thanks a lot. Welcome everyone. And yeah, go ahead.
Okay, thanks, Thomas. Yeah, so this is joint work with Srinivasan, Arunachalam, Alexander Belovs, Andrew Childs, Robin Kothari, and Ansis Rosmanis. And indeed, part of this work was done in this wonderful summer of 2018 at the Simons Institute, the previous quantum program. So this is about coupon collecting, and coupon collecting, of course, it happens in theory, it also happens in practice. So every year, the Dutch supermarket chain Albert Heijn, this is kind of the Safeway of the Netherlands, the biggest, well, one of the biggest supermarket chains, they hand out these cards of soccer players. I guess in the US they would hand out baseball cards, but in the rest of the world, people care more about soccer. And if you spend €2.50 at their supermarket, you get one of these cards uniformly at random. And there are 18 teams in the Dutch soccer league, 11 players per team, so that would be 198 different cards. Actually, I'm making up these numbers here because probably they will have more than just 11 cards per team, since there's also like people sitting on the bench, etc. But let's say 198 different cards. And let's say your nephew really cares about getting a complete set. So they want to have at least one copy of each of these 198 different cards. So how much money would you need to spend at Albert Heijn in order to get each card? Now, clearly you would need to spend at least $2.50 for each of these cards, right? Because every $2.50 that you spend will only give you one card. So you need to spend at least the number of cards. 198 times €2.50 is 495 euros. But the situation is unfortunately much worse, because if you have already almost all of the players, let's say you're just missing one great player, everybody else you already have a copy of their card, and you go to the Albert Heijn to spend another $2.50. Let's say you're buying some toilet paper to sustain you through the lockdown. What are the chances that this one randomly chosen card that they will give you is actually the one that you didn't have yet? It's a very low probability, right? So you go to the Albert Heijn, you spend $2.50, and you get a card you already have, and you're very unhappy. You go again to the Albert Heijn, defying the lockdown, spend another $2.50, get another card. You probably already have that one as well. So why is this happening? It's because initially you're making a lot of progress in this coupon collector problem because you haven't seen any cards yet at the beginning. So the first card that you get is definitely new. The second card that you get is probably different from the first one. The third one that you get is probably different from the first two, and you're making rapid progress. But then near the end, you're making very slow progress. And there's a very nice mathematical analysis in expectation of how many of these coupons you need to draw uniformly at random, because before you've seen every coupon at least once. Right? And this is really an exercise in one of the first few lectures you see in a probability theory course. It's very clean. Let me show it to you. So suppose that you have already seen I out of the k possible coupons. So k would be 198 here, the total number of coupons. You'd like to get one copy of each coupon. And let's say you have already I different coupons. Right, so there's k minus I coupons left, or k minus I soccer cards left that you would like to get. And you're given one of the k cards uniformly at random. So the probability that your next coupon is a new one that you haven't already seen a copy of, is k minus I divided by k, right? Super elementary probability theory. And that means that if you look at the expected number of samples you need before you see your first new coupon, it's the reciprocal of this probability, right? So if you have probability P of having a success, then the expected number of tries before your first success is 1 over P. So if you already have seen I out of the k possible coupons, you need roughly an expected number of k divided by k minus I new samples before you get your new, the first time you get a coupon that you didn't already have, or a soccer card that you didn't already have. And you can add up these expectations because, so when I is 0, the expected number of trials is just 1. When I is 1, the expected number of trials is k divided by k minus 1, etc. So you can just add this up over the total number of coupons you would like to get eventually. And so this becomes the sum of I running from 0 up to k minus 1 of this expected number of samples needed to get your next coupon. And this is a very simple sum. So you can rearrange it a little bit. You pull out the k out of the sum, you rename k minus I to j, and now you just have k times a harmonic series, and the harmonic series, of course, is essentially the natural logarithm of k. So the expected number of samples, you can determine it quite precisely. It's k times natural logarithm of k plus an order k term, so that's a lower order term. And this is substantially bigger than k. Right, so for instance, if k is 198, as in my soccer cards example, that's 1162 samples. So instead of just spending 250 for each new card, you actually, especially at the end of the process, have to spend massive amounts of money to finally see all the coupons. And the reason is you're making very slow progress at the end. Right, and 1162 samples times 2.5 euros per sample, that's almost 3,000 euros. That's much more expensive than if you could just sort of choose which cards you buy for your 250. And I'm sure the supermarket chain is aware of this. This is, of course, a trick to get you to spend more and more and more. And you're unlikely to finish earlier. Let's see. You're unlikely to finish earlier because you can calculate the variance in this number of samples, and it's on the order of k squared. Which means that the number of samples you will actually have to do, right? Previously, we just calculated an expectation, but the number of samples you actually have to do before you've seen everything at least once is k ln k plus an order k term. So you're very unlikely to be lucky and to use a number of samples that's much smaller than k ln k. And this is a quantum talk. So of course, my question is, can quantum somehow help in this process? And of course, if you're just given random samples, there is no quantum there. There's really nothing much you can do. So there the answer would be no. But let's broaden the scope a little bit. So suppose that instead of uniformly random samples over the k soccer cards or the k coupons, you're going to get quantum samples. And a quantum sample would be sort of the coherent analog of a random sample. So that's just a uniform superposition over the set S. So let's say that we have a universe of size n, and there's k, there's a set of size k in that universe, and you'd like to collect every number in that set S. So there's still k coupons, and somehow they live in the universe of size n. And your sample, your coherent sample, would now be a uniform superposition over all the elements of S, right? So ket S would be 1 over root k, and then just a sum over the basis states over all the i's that are in the set S. So you're given such a state, you're probably given multiple copies of such a state, just like in the classical case, you would be given multiple random samples. And then your goal is to kind of do a quantum measurement and try to extract the set S as quickly as you can, meaning using as few copies of this state ket S as possible. Now, one thing you could do with this state, of course, is just to measure it. It's a stupid thing to do, but you could do it. What happens if you measure it? Well, you just get back to the classical situation of uniformly random samples from S, right? And we know by the analysis of the previous slide that the number of samples needed is essentially k ln k, plus some lower order term. But of course, we know that if you want to get your quantum magic to perform, you need to do something clever before measuring. So the question I'm going to ask here is there something smarter that we could do that would use fewer than k ln k copies of the state S in order to recover the set S. And let me give you the short answer though, so it's a yes/no answer. So the answer is yes, if the size of the set is kind of close to the universe size. So I'm going to use the letter M for the number of missing items, meaning the number of elements of the universe that are not in the set S. So that's n minus k. And it will turn out that you can get an improvement for quantum coupon collector, meaning you can get by with far fewer than k ln k copies of ket S if this number of missing items is small. And if the number of missing items is big, the answer is going to be no. So that's what I'll spend most of this talk on explaining the positive and the negative. I will start with the, maybe I should pause a second here to let you read this. And like Thomas said, if there's any questions, just interrupt me. Or you can type in the chat and then Thomas can relay it to me. Okay, no questions at this point. So let me first explain the positive part. So if we're trying to reconstruct a set of size k and k is very close to the universe size n, then it will turn out that you can beat this classical coupon collector. So that's what I'll explain now. And the trick here is that you can learn the set S by learning its complement, right? So the universe minus the set S. And if there's few missing elements, then the universe minus the set S is a small set. And what we're going to do is we're going to show how you can take a number of copies of the state ket S and convert this into essentially a uniform superposition over the complement of S, from which you can then sample by just a measurement. And recovering the small complement of S is much more efficient than recovering S itself, just because there are few elements in this complement. So how does this work? Well, we're given the state ket S, in fact, a bunch of copies of them. And the trick is to observe that the state ket S can be written as a linear combination over the whole superposition. I hope you can see my mouse. So by this ket brace n, I just mean the uniform superposition over all the n elements in the universe. So your state ket S is a linear combination of this uniform superposition over the whole universe, plus some state ket psi, which is orthogonal to this uniform superposition. And you can see the weights here. So the weights of the uniform superposition over the whole universe, the amplitude is root k over n. That's pretty close to 1 because k is pretty close to n. And then there's this root m over n, which is the amplitude for the state ket psi. And this ket psi, it has this form. This is just a sort of a dumb calculation that you can do. If you define your state ket psi like this, then S is this linear combination of the whole uniform superposition over everything and the state psi. And the state psi is interesting. Why? Because it has a lot of weight. K over n is almost 1. It has a lot of weight over the uniform superposition of S complement. So essentially the state psi is negative, the uniform superposition over S complement, assuming indeed that, that m is much, much smaller than n, equivalently that k is kind of close to n. So let's try to take a bunch of copies of ket S and try to convert these into one copy of psi, from which we can then sample, and this will probably give us elements of the complement of S. So what do? We take one copy of this ket S, sort of a coherent quantum version of a random sample over the coupons, and we measure it with a 2-outcome projective measurement, where the first operator is just a projection on the uniform superposition over the whole universe, and the second projector is just everything else. So the n-1 dimensional complementary space. You can calculate the probabilities of the 2 possible outcomes, and because the amplitude of ket psi in this decomposition is root m over n, if we do this measurement on one copy of ket S, then with probability m over n, it's kind of small, but okay, but with probability m over n, we obtain one copy of psi. And we know when we succeeded, right? Because this projective measurement is going to tell us whether the outcome was the first or the second possibility. And if it's the second possibility, we're happy because we've obtained a copy of the state psi. But we only succeed there with small probability m over n. But you can just repeat this, right? So you can just repeat this using n over m copies of S or ket S, or rather an expected number of n over m copies of ket S. You do this measurement on all of these copies, and with high probability, one of those is going to succeed and give you a copy of psi. And psi is essentially a uniform superposition over the complement of S, up to small error, which I'm going to ignore in this talk. Right, and if you can make a uniform superposition over the complement of S, you can just sample from that. You can sample from the complement of S. You can do that a number of times. And now you're back in the situation of the classical coupon collector, but on a much, much smaller set, namely S complement instead of S itself. Right, and S complement has just M elements, which means that just by classical coupon collector, roughly M log M copies of this state, which is uniform over S complement, suffice to recover the whole set S complement. And if you have S complement, you also know S itself, which is the goal here. And now we needed roughly n over m copies of the starting state ket S to produce one copy of ket S complement. So in total, we're going to use something like n times log m many copies of ket S for a quantum coupon collector. And notice that what we're doing here is very simple. We're not doing some fancy non-product measurement on the tensor product of all of these copies of S. We're just doing state-by-state measurement. Right? We just do a very simple measurement on each copy of S. A few of those succeed, and then we just measure in a computational basis the resulting states for the few measurements that succeeded. And this is going to give us S complement. And the point here, of course, that if M is very small, let's say M is constant, then only order n copies of ket S suffice for the quantum coupon collector, in contrast to the n log n. Right, so this is the situation of the positive result I mentioned before. If the number of missing elements is small, so if n minus k is small, then you can beat, then using coherent quantum samples, you can beat the classical coupon collector by a log factor. And this is, so there's two ways to look at this. You can either think of this as a sort of a kind of acute quantum measurement problem. But of course, if you'd like to attract the attention of venture capitalists, you would call this quantum machine learning, right? Because you're just actually learning something here. You're learning the set S. And you can do that quite efficiently. And what I want, so let me just pause again for questions, because after this, I want to show that this upper bound on the number of copies is actually tight. So if there's any questions, now would be a good time to ask them. I'll take some tea in the meantime.
Hi, Ronald. I wanted to ask, so in this S state, why is it square root k over n times this n? So shouldn't it be like k or something? Like,
why would it be k?
K?
You can just calculate.
Yeah, so this is the uniform superposition over everything.
Yes, with amplitudes 1 over root n for each element.
Ah, okay.
So ket n is normalized and ket psi is also normalized.
I see. Ah, okay. Thank you.
I mean, this is just a calculation. You can just verify that this equation holds. It's not super insightful, but the good thing is that it allows you to somehow extract a copy of S complement from a bunch of copies of ket S.
Okay, thanks.
Okay, so this quantum coupon collector, it can, at least this upper bound says that you can beat the classical coupon collector by a log factor if m is very small. On the other hand, if m is polynomial in n, then this quantity here is just the same n log n that you would also have in the classical case. So in that case, at least this setup, this algorithm, this measurement scheme, it doesn't beat the classical coupon collector. And what I want to show in the next few slides is that this upper bound is actually tight. So this is the negative part of the talk. You can only hope to beat the classical coupon collector using quantum coherence if m is very small. Right, so I'm now going to go to the lower bound part, lower bound on the number of copies of ket S you need to recover the state S, the set S. So matching lower bounds, I mean matching up to constant factors. So here's the claim. This is what I already said. So let's assume the number of missing elements is at most half, right? Previously, we saw the interesting cases where m is very small. So let's assume m is no bigger than half of the universe. So the size of the set k you're trying to recover is at least half of the size of the universe. So I claim that you need essentially k log m many copies of the state cat S in order to learn this, the set S itself, right? And this matches the upper bounds of the protocol of the previous slide. So how do you prove something like this? So our approach is to use the so-called adversary lower bound. And this might be slightly mystifying because the adversary lower bound is a lower bound in quantum query complexity. And there's no queries here, right? The only thing that's happening here is we're given a bunch of copies of the state cat S. So for every S, there's like a state, which is a T-fold tensor product. And we just want to distinguish those states. And you might think, and we thought so as well, you might think that a better approach here is to use just a very good measurement. And what is a very good measurement? Well, of course, we have no idea what the optimal measurement would be for this system here, where you're given T copies of cat S and you want to learn S. But there is this thing called the pretty good measurement, which is also known as the square root measurement. And it's known that this measurement, which you can just write down, you can write down its POVM elements. This measurement is known to have a success probability that's only quadratically worse than the very best possible measurement. Right, so if the very best possible measurement, which maybe you don't know, has success probability 90%, then this pretty good measurement, which you do know, has success probability at least 0.9 squared, which is 0.81%. So if you don't really care about the constant factors, that should be good enough to analyze the behavior of the so-called pretty good measurement in distinguishing the different possible states, where by states I mean T-fold tensor product of the state cat S for all the different possible sets S. So we tried this first, and it leads to very complicated formulas that we expended a lot of effort on, and we couldn't really analyze it. So instead, I'm going to use this adversary lower bound, which is a query complexity lower bound, and I'm going to use it without any queries. And why on earth is this possible? Well, it's because this adversary lower bound, this is due to, in its original form, due to unbiased, and then it was extended by Oyerli and Spalek, and then worked on further by people like Rijkaard. It has been generalized to also give a very good tool of analysis for state transformation problems. And in a way, what we're trying to solve here is a state transformation problem where we're starting with a state that's T-fold tensor product of the state cat S. And we somehow want to transform this to just a classical description of S, right? Let's say just a 0-1 vector with support on the elements of S. So this is a state transformation problem, and this is actually something that the adversary lower bound can characterize. And the way to apply the adversary lower bound is to set up a bunch of matrices and look at various norms of these matrices. So that's what I'll do now. So let's first consider the gram matrix of the different states that we want to distinguish. Right, so for every case set S, there's going to be a state like this. And you can have a matrix M indexed by the different sets S, so that's an n choose k by n choose k matrix. And as the entries of this matrix, so let's say the rows are indexed by elements S, and the columns are indexed by elements S prime. At the S, S prime entry of this matrix M, you just put the inner product of the state with S and the state with S prime. And because these are T-fold tensor products, these inner products are just the Tth powers of the inner products between S and S prime. Right, and notice that the inner product between S and S prime, cat S and cat S prime, really only depends on the intersection size of S and S prime. So this property is going to be important soon. So this is the gram matrix M, which sort of characterizes the overlaps between the different states that you're trying to distinguish in this problem. Now let's define another problem here, another matrix of the same dimension. So n choose k by n choose k. And this is a very simple matrix. It's just sort of the photo negative of the identity matrix. So it has zeros on the diagonal and it has ones off diagonal, right? So you can think of this as the all ones matrix minus the identity. So that matrix I call F. And you can immediately get from this, from sort of general machinery that's known about the adversary lower bound, that the state transformation problem that we are trying to solve can be solved with high success probability if and only if the so-called gamma-2 norm of the Hadamard product, the entry-wise product of these two matrices, is small. Right, so you have the matrix M, this gram matrix, it's an n choose k by n choose k matrix. You have the matrix F, which has zeros and ones of the same dimension. you can take the Hadamard product of these two matrices. This will really just zero out the diagonal of M, because F is everywhere 1 except on the diagonal. And then you look at the so-called gamma 2 norm of this resulting matrix. And you should think of this gamma 2 norm sort of as the minimal error probability of any measurement scheme. So the state transformation problem can be solved, meaning there is a good measurement to distinguish all these states, if and only if this gamma 2 norm is small, let's say 0.1 or something like that. And I don't want to define the gamma 2 norm itself, but rather look at its dual, because the dual norm, because that's easier to manipulate for us. So you can alternatively define so this is the dual formulation of the gamma 2 norm of the matrix M circle F. So this is the maximal operator norm you can get if you maximize over all so-called adversary matrices. These are just any matrix of the same dimension. So you maximize over matrices gamma, whose operator norm is at most 1. You look at the Hadamard product of gamma with the matrix M circle F, and you maximize its operator norm. And this looks kind of complicated, but you can show that if this quantity is small, so if the gamma 2 norm of M circle F is small, then you can actually solve the the state transformation problem with high success probability, with low error probability. But the good thing about this dual formulation is you can also use it for a lower bound. Right, so let's say that we fix our t, we want to prove a lower bound, so let's say that we fix our t, the number of copies, to be too small. Then there shouldn't be a good measurement scheme, there shouldn't be a good state transformation scheme, so the gamma 2 norm should be big. And this is something you can prove by just exhibiting one adversary matrix. Right, if I can find one particular matrix gamma that makes this operator norm of gamma circle M circle F big, let's say a half, then that shows that if I use these t copies of my state cat S, no matter what I do, my state distinguishing protocol will always have a large error probability. So this is how we're going to use a lower bound. We're going to exhibit a specific adversary matrix to show that gamma circle M circle F has large operator norm. And how do you approach something like this? Well, you need to use symmetries. So how do you construct such a gamma? The thing to observe is that the matrices M and F that we care about here, they have a very nice symmetry, namely that the S, S prime entry of both of these matrices just depends on the intersection size of the sets S and S prime. Right, so for M, looking here, this should be kind of obvious, because if you look at the inner product between the state cat S and the state cat S prime, this really only depends on the number of elements that are common to S and S prime. So clearly the entries of the gram matrix M are only dependent on the intersection size of S and S prime. And the same should obviously be true for this matrix F, because here the only things that are 0 are the elements on the diagonal, where S equals S prime, and all the other elements of F are 1. So the matrix M circle F that we want to analyze, it has this nice symmetry, and in order to find a good, or to construct a good adversary matrix to witness that this norm here is big, we need a kind of mathematical toolbox that respects this symmetry. And the mathematical toolbox to use is the so-called Johnson association scheme. And this comes back in all sorts of branches of mathematics, sometimes under the name of Bose-Messner algebra. It also has to do with the Johnson graph that is used in quantum walk algorithms. So what is the Johnson association scheme? It's essentially just a set of matrices, which can be characterized in different ways. So let's first define Boolean matrices, A0 up to AM, of the same dimension as before, so n choose k. So these matrices have the same dimension as the M and the F that we care about. And let's say that these matrices, we define them to be indicators of a specific intersection size between S and S prime. So AJ is going to be a Boolean matrix, and I'm going to set the S, S prime entry of this matrix equal to 1, if and only if the intersection size of S and S prime is equal to k minus j. Right, so this way I'm defining these different sort of intersection intersection witnessing matrices, A0 up to AM. They're very simple matrices. They're all 0-1 matrices and they don't overlap. So if you take, let's say, AI circle product, Hadamard product with AJ for I different from J, you're just going to get 0. Because if AI is a 1 in a certain position, it means that S and S prime and at that position have a certain intersection, and it means that AJ will have a 0 there because S and S prime cannot have 2 different intersection sizes at the same time. And then you can look at sort of the linear span of these matrices, so everything you can get by linear combinations of A0 up to AM, and this forms an algebra. And a different way to characterize the same algebra, or rather to have a different basis for the same algebra, is there also exists pairwise orthogonal projection matrices, projectors of the same dimension again, E0 up to EM, and they span the same space. And that means that every AI matrix can also be expressed as a linear combination of the projectors EJ. And the coefficients in this linear combination, those are called the eigenvalues of the Johnson association scheme. And conversely, you can also express the EJs as a linear combination of the AJs just by inverting this linear transformation here. So every EJ, you can write it as 1 over capital N, that's the dimension of the matrices, times a sum over the AIs with coefficients QJI. And these numbers here, they're called the dual eigenvalues of the Johnson scheme. And most importantly, you can also express the Hadamard products of EI with EJ as a linear combination of ELs. And the way to see this is as follows. I already mentioned before that if you look at the circle product of AI with AJ, then this is going to be the 0 matrix unless I is equal to J. And if I is equal to J, you just get back AI itself because 1 times 1 is 1. So that means it's clear that the circle products of the A matrices can be expressed as A matrices, but then by these linear transformations, it should also be possible to express the circle product of EI with EJ as a linear combination of AIs and also of ELs. And the coefficients in that linear transformation, in that linear combination, those are called the so-called Krein parameters of the Johnson scheme. Right, so for every pair EI, EJ, on the left-hand side, you have the entry-wise product of the matrices EI and EJ. On the right-hand side, you have some linear combination just of the matrices EL. And the coefficients here, those are called the Krein parameters of this Johnson scheme. You can actually derive them with a bit of effort from the eigenvalues and the dual eigenvalues, but you don't have to, because these parameters are all known, and you can look them up in fancy yellow books.
Sorry,
yeah.
I didn't get, why are they not just products? So E is expressed as a linear combination of AIs, and you said the AIs are basically orthonormal with respect to the Hadamard product? So is that what you said?
Yeah. So the AIs are pairwise orthogonal to each other. In fact, they are, like if you multiply them entry-wise together, you get 0 or you get the old.
Right. So if I compute the Hadamard product of EI and EJ, it'll simplify, right? It'll be very simple. I'll only get.
Well, I mean, suppose you want to sort of derive these Krein parameters from the eigenvalues and the dual eigenvalues. What would you do? You would look on the left-hand side here, EI circle product EJ. We have an expression for EI and EJ in terms of the AIs.
Yeah.
You plug that in here. You get this big linear combination with a sum over I and J of all the circle products of AIs with AJs. And then indeed things simplify.
Yeah.
But you still have kind of fancy coefficients in front there. So these Krein parameters, they're not so easy.
Okay. Okay. Never mind. It's a side.
Yeah. The good thing is though, we didn't have to figure them out. You can just look these things up in books. Okay, now how does this relate to what we're trying to do? Let me remind you of what we're trying to do. Right, so we have this matrix M given by the inner products between the states we care to distinguish. You have this matrix F, which is just a photonegative of the identity matrix. And we want to show that M circle product F has large gamma 2 norm. And we want to do that by exhibiting a particular matrix gamma, whose operator norm should be at most 1, such that gamma circle product M circle product F has large operator norm. and by large, think at least a half. So that's what we're trying to do. Right, so like I said, the entries of the matrix M, they only depend on intersection sizes, and that means you should be able to express them as a linear combination of these AI matrices. Because the AI matrices, they're just 0, 1 matrices that sort of indicate whether S and S prime have a certain intersection or not. And this is easy to do, so you can easily express M as a linear combination of the AI matrices. But the AIs themselves are linear combinations of the EJ matrices, so you can also express M as a linear combination of the EJ matrices. And what is our adversary matrix going to be? It's also going to be a linear combination of the EJ matrices. So I'm going to pick parameters gamma j. I'll say what they are in a moment. Such that gamma here, this gamma matrix, the adversary matrix that we want to construct in order to witness the large gamma 2 norm of M circle F. I'm defining gamma like this. It's a linear combination of the EJs with parameters gamma j. And I'm going to choose the gamma j's like this. So gamma 0 up to gamma m minus 1. So everything except for the last one, they're all equal to 1. And gamma m, I'm going to choose to be some number between minus 1 and 0. So everything is 1 except for the last coefficient, which is a little bit below 0. And this has some good features. So one thing to observe here is that, remember these EJs, they're pairwise orthogonal projectors. And that means that the largest eigenvalue of gamma, the operator norm of gamma, that's just the largest coefficient gamma j. Right? If you have different projectors, it's like you have sort of a block diagonal matrix. Each block multiplied with gamma j. And the maximum gamma j, that's going to be the operator norm of gamma. And remember, an adversary matrix gamma, one property it needs to have is operator norm at most 1. But I'm choosing all these gamma parameters to be equal to 1 or at most 1 in absolute value. So it follows that, that our gamma matrix defined in this way has operator norm at most 1. That's a good thing. Another important property of this construction, and this is how the choice of gamma m is determined. So the gamma m is the only parameter which is not equal to 1. It's in fact a little bit below 0. This is determined in such a way to ensure that the diagonal entries of gamma are all equal to 0. So I want to explain how this works, but you should think of epsilon m, em, the last projector in this linear combination, as being sort of by far bigger than everything else. And that means that by choosing gamma m, you can kind of steer the trace of the matrix gamma. And it turns out that all the entries on the diagonal of gamma are equal. So if you can make it to have trace equal to 0, then actually the diagonal entries of gamma will be equal to 0. So I'm skipping a bit of detail here, but I'm choosing this parameter little gamma m to ensure that all the diagonal entries of gamma are 0. Why does this matter? It matters because if I now take the entry-wise product of gamma with f, remember f is the matrix that has zeros on the diagonal and ones elsewhere, then this leaves gamma invariant, right? If gamma already had zeros on its diagonal, I can multiply entry-wise, I can multiply it with f, but it doesn't change anything. So gamma circle product f is equal to gamma. And this is good. Again, let me remind you what we're trying to do. We're trying to show that this matrix here, gamma circle m circle f, has large operator norm. Now, by my choice of gamma, and because this circle product is commutative, this f sort of drops out. You can put it here, you can entry-wise multiply it with gamma, it just disappears. So the only thing left to care about is lower bounding the operator norm of gamma circle m. And now, so why do these crime parameters come in? The reason is gamma is a linear combination of the EJ matrices. M is also a linear combination of the EJ matrices. So if you take the circle product of gamma with M, you get a linear combination of circle products EI with EJ, which using the crime parameters, you can translate back to a linear combination of just the ELs. And then you can just read off the largest eigenvalue of the resulting matrix as the largest coefficient in this linear combination of ELs. Because every matrix that's a linear combination of the EL matrices, its operator norm is just the largest coefficient in that decomposition. So all that's left to do now, and I'm not going to sketch that, it's a kind of a long calculation, which even involves calculations similar to what you see in classical coupon collector. But the bottom line of that calculation is that if the number of copies T is much less than K times log M, then in fact, the first coefficient, if you express gamma circle M in terms of the ELs, the first coefficient is already at least a half, meaning that the operator norm of gamma circle M is at least a half. And this establishes the lower bound, because this operator norm being big means that every possible measurement scheme that tries to take T copies of ket S and learn S from this must have a large error. So this ends the lower bound part that I wanted to talk about. Again, a good time to stop for questions. Okay, so now I want to, and maybe I should have done this first, but I want to, so this kind of concludes what I wanted to say about the quantum coupon collector, right? So the upper bound part shows that using roughly K log M copies, you can recover S, and the lower bound says that this number of copies is tight, up to a constant factor. And now I want to give a bit of motivation for why we cared about this, this kind of type problem. And the motivation comes from PEC learning, probably approximately correct learning. So let me just explain how this quantum coupon collector and the fact that it beats classical coupon collector, how this says something interesting about PEC learning. So what is a PEC learner for a concept class? So let's say you're trying to learn a function, a Boolean function on a domain of size n, and you have a class of possible functions, right? So there's an unknown function coming from this class and you're trying to learn it. And how are you trying to learn it? Well, you're given examples of this function, sort of points in its truth table. So an example, and I'm talking classically here, an example is just a pair x, fx, where x is distributed according to some unknown distribution d. And you can think about this d as sort of nature or some process that generates your data. So there's an unknown target concept f, and you're given examples, multiple examples that of this form, where x is distributed, in every example, x is distributed according to the same unknown distribution d. So d is a distribution on this set here. Right, and your goal is to learn f, and that's usually too much to ask, so your goal is to learn f approximately. And even that is probably too much to ask, so you're asked to probably approximately correctly learn f, and that's what PEC learning is all about. So your goal is to find a hypothesis h, that's some other function, hopefully close to f. And close to f is measured in the following way. So for every possible target function that you're trying to learn, for every possible data generating distribution d, the probability, if you were to draw another example according to the distribution x, the probability that your hypothesis h misclassifies that example compared to what the unknown target function f does, that probability should be small. It's at most epsilon. So a good learner achieves this with high probability, let's say probability 2/3. Right, so just to repeat, what a PEC learner should do is you should take a number of examples of this form, hopefully not too many, use those to somehow produce a hypothesis h, which is some other function, and this h should disagree with the function f you're trying to learn only with probability epsilon, where that probability again is taken under the unknown data generating distribution. And this is kind of important. It's important in PEC learning that the examples are generated by the same distribution that's eventually used to kind of evaluate whether you learned well or not. Right? This is like having a, let's say if you have a history teacher who really focuses on World War I and just he fills his lessons with lots of stuff from World War I, but then on your exam you get only questions from World War II. That's not fair. So it's important here that the final sort of measure of correctness of your hypothesis is according to the same data distribution d that generated the examples. So that's the goal of PEC learning, and there's a massive amount of theory about this. And there's one very fundamental theorem about this, which kind of characterizes information theoretically the number of examples you need to achieve PEC learning. And it says that the required number of examples is up to a constant factor equal to the so-called VC dimension of the concept class C you're trying to learn. I won't explain what that is, but it's some combinatorial measure of complexity of the concept class that you're trying to learn. So a class that's very big, that has very many complicated functions, this will have a bigger VC dimension than a very simple concept class. So the number of examples you need is this VC dimension divided by the epsilon accuracy that you want. So if you want to learn with and to be fairly sure that your overall error at the end is at most 1%, the number of examples that you need scales like roughly 100 times the VC dimension. And this is really a cornerstone of computational learning theory. And the fundamental theorem has the property that if you want to achieve it, so there is always a learner which learns well using at most as many examples. But the learner sometimes has the property that the good hypothesis H that it outputs is not itself an element of the concept class C. It's a so-called, so you should allow so-called improper learners here. And you can, of course, try to restrict the learning algorithm further, not only that it should output a good hypothesis, so something that's close to F in this sense, but also that it should be restricted to only outputting hypotheses that are in the class C from which your target concept comes. Right? So let's say that you're trying to learn neural networks, then the only thing you're allowed to output is a neural network, not a decision tree. That would be called a proper learner. And it's known in classical computational learning that the fundamental theorem fails if you enforce your learner to be proper. So requiring A to be proper in some cases can significantly increase the sample complexity of the problem. You just need more examples if you want to have so much data that you can actually output a good hypothesis from the concept class C. And a simple example is actually based on coupon collector. So there is a concept class C, I'll explain in a minute what it is, where a proper learner needs VC dimension C over epsilon times another log factor, log 1 over epsilon, many examples. Right, so asymptotically, this is more than what the fundamental theorem says. So requiring learners to be proper can increase information theoretically how much data you need to learn. And here's an example. So let's consider the coupon collector problem in this very simple case where you have a universe of size n, and the set S you're trying to learn has size n-1, k is n-1. So there's really only one missing element. So there's the set S that you want to learn, its complement S complement has size 1. So effectively, you're just trying to learn one missing element. And you can look at the set of functions that are indicators of such sets. And this is a very simple concept class. If you look at the truth tables of such functions, it's just a column of ones with a 0 in one position. So this is a simple concept class. In effect, its VC dimension is just 1. But let's say that we want to learn this concept class with a very small error, epsilon set to 1 over n. And let's say you consider distributions that are uniform on the support of Fs. And then classical coupon collector implies that for this class here, you actually need n log n samples, right? And that's asymptotically bigger than VC dimension over epsilon, because VC dimension over epsilon is only n in this case. So forcing the learner to be proper, meaning that you have to output a function of this form, or equivalently, you have to output a set S, the right set S with one missing element. This actually sort of boosts, increases the required amount of data by a log factor and makes it asymptotically bigger than what the fundamental theorem says. And the interesting thing is that this separation, so this is one of the few examples that we know that separates proper and non-proper classical PEC learning. This example fails in the quantum case where you're given coherent examples instead of random examples. And that's just in disguise the upper bound that I mentioned before. If you're trying to learn a set S with one missing element from uniform superpositions over that set, order n copies of the set suffice instead of n log n. And this leaves open an interesting question. I mean, this is really just a starting point, but it's really just, this leaves open the interesting question. Maybe it's possible that in the quantum case, proper and non-proper learning are the same in terms of sample complexity.
Ronald, there's a question. Zeph, I don't know if you want, okay, so the question says, what is the H for this example in the improper case? So I think they're asking what's the H that the improper learner would learn using.
I guess, so the distributions you would consider here would be the ones that are, yeah, okay, so I guess, I mean, so every fs in this set, its truth table is a column of ones with 1 0 at one special place. And all of those functions are very well approximated by the constant 1 function. So what the improper learner would do is it would just output the constant 1 function. And under all the distributions we consider, this has a small error compared to the function you're trying to learn, but it's not in the class. So the all ones function is not in this class C. So there's kind of a trivial improper learner. But if you want to do proper learning, you should really identify the set S completely, because you're supposed to output an element from this concept class, and you can show under certain distributions that if you output any other element from the concept class, your error will be bigger than epsilon, which you're not allowed to do. So by setting epsilon so small, we're sort of forcing the proper learner to really learn the set S, and then you're just sort of you're in a thinly disguised version of the classical coupon collector problem. I see the number in the chat going up, so maybe there's more questions you want to read to me.
No, Zeph says thanks. That's why it went up.
Oh, okay,
so I think your answer was good. Thanks.
Yeah, so I think this example, even though this is what motivated us to study this quantum coupon collector, I think this is somewhat unsatisfactory because it raises the interesting question whether quantumly proper and improper learning could be equivalent in terms of sample complexity. And we're not answering that question at all. It's still an interesting open question. The only thing we're doing is we're sort of destroying the one example we know classically that separates proper and improper learning. Okay, so one last slide before the summary. So one of the things we actually did at Simons in summer 2018 is generalize this model a little bit by considering the case where you're not only given copies of the state S, ket S, but you also have the ability to reflect through the state S. What I mean by that? Well, it's kind of not unreasonable, because if you have a machine that can give you copies of the state ket S, it might well be that you actually have a unitary which can convert an initial state ket 0 into ket S. And if you have such a unitary, and you can do U as well as U inverse, that's good enough to reflect through the state S. So by reflecting through the state S, I mean some unitary that maps ket S to ket S, and anything orthogonal to ket S to minus itself. So let's just assume that in addition to having copies of ket S, you can also reflect through the state ket S. And this makes you a lot stronger in terms of quantum power, because it means you could do things like amplitude amplification to kind of zoom in on the set S more quickly. Right, so the goal is still this learning task. There's an unknown set S of size k in a universe of size n, and our quantum algorithm should learn the set S. And if you can reflect, you can do that faster than if you just have copies of ket S. So I want to show that now. So again, just like in the case of our optimal measurement scheme, we're not going to find the elements of S directly, but rather we're going to find the elements of S complement. And the way we do that is by amplitude amplification. So we start with a uniform superposition over all the elements in the universe. That's easy to construct. And then using amplitude amplification, we can actually rotate this to a uniform superposition over the complement of S. You can do this using amplitude amplification, and the cost of this is something like square root n over m. This is very standard, so I won't explain the details. So you just generate uniform superposition over the complement of S, you measure it, you get your first element in the complement of S. And now you want to do this again, but instead of generating the state which is the superposition over the complement of S, you want the complement of S except this one element that you already have. So you're now rotating to everything in the complement of S that you haven't seen yet. And this is going to have amplitude amplification cost square root of n minus 1 divided by m minus 1. You measure this state, you get a new element in S bar. And the point is that I1 and I2 are different here. They're guaranteed to be different. So you're avoiding this annoying thing that you have in coupon collector, that at the end, you're very unlikely to see new elements. This we just avoid using amplitude amplification. And you just keep doing this until you've seen all the elements of S complement, and then you know both S complement and S itself. And what is the cost of this? Well, you just sum up the cost of these amplitude amplifications over all the steps. By cost, by the way, I mean the number of reflections we use, for the number of applications of U and U dagger. And this turns out to be asymptotically square root k times m. And this is significantly faster than if you just have copies of cat s available. We also show that this is tight. We also get a bound for the other case. So again, I'm assuming here that m is not too big, so that most half the universe. We have another bound which is also tight for the other regime. So this brings me to my conclusion. I think this is sort of well timed. So summary, classical coupon collector, what is it? There's a set of size k in a universe of size n, and you want to learn it from uniform samples over S. How many do you need? K log k. Quantum case, you want to learn, again, the same set S of size k from a universe of size n. And now you're, instead of given uniform samples, you're given coherent quantum examples. So uniform superpositions instead of uniform samples over S. And now it turns out that the number of copies of the sample that you need, so the number of coherent samples you need is roughly k times log m, which in particular means that for small m, you beat the classical coupon collector. There's something substantially smarter you can do with these quantum states cat s than just measuring them. And it's smarter, but it's not super fancy because, like I emphasized when I described the scheme, there's nothing sort of non-product going on here. You just get a state cat s, you do a simple measurement. If you succeed, you measure the resulting state in the computational basis. You do this state by state, and that just gives you set s eventually. We also have tight bounds for learning the set s if additionally you can do reflections through the state. And let me end with this open problem here. Are the quantum sample complexities of proper and improper PEC learning the same for all concept classes? I think this will be quite an intriguing result. We can't prove that. The only thing we did is we removed the example that disproves this in the classical case. Yeah, so that concludes my talk. I can't hear you, Thomas.
Oh, I said thank you, Ronald, and I also clapped.
Okay, thanks.
Everyone is doing, but they're not unmuting themselves. So
yeah, I can't see anything except for you.
Yeah, so I mean, anyone questions? Maybe while they think about it, I had one very naive question. It's a bit simple. Maybe while they think about it, I had one very naive question. It's a bit simple. I heard myself with
yeah, I heard it.
Okay, this was very strange. I heard myself. But I think this is because.
Should I mute myself?
No, it's because Andras wanted to ask a question. Andras, do you want to ask your question? I can ask myself my question after.
Go ahead, Andras.
Okay, thank you. So I wanted to ask this example that you showed, Ronald. So there, yeah, in this improper versus proper learning, you basically concluded that there is like a logarithmic overhead.
Right.
But what if you choose like epsilon to be a much smaller epsilon, and still this trivial function that you mentioned seems like a good candidate. So it seems that you have much bigger separation in that case when epsilon is, I don't know.
Well, I mean, so picking epsilon much smaller means picking n much bigger, right? So we're choosing epsilon to be 1 over n here. And n essentially defines epsilon, and therefore it defines the size of the coupon collector problem you need. And then the number of examples that you need scales like log 1 over epsilon, which is the same as n log n. So it's not that you can improve this to n log squared n or something like that. So expressed in terms of n, it's always n log n.
But why can't you just choose epsilon to be, I don't know, 1/3 independent of n?
If you choose epsilon to be 1/3, then both in the classical and the quantum case, order 1 example suffice. So you get an asymptotic separation here in terms of the dependence on this epsilon. So in the non-proper case, you have a dependence which is linear in 1 over epsilon. In the proper learning case, you have a dependence, at least for this example, that has an extra log 1 over epsilon factor here. So you only see an asymptotic difference for small epsilon.
So the intuition here is that things become difficult when you reach this regime where basically you only need to find a few rare elements missing from your set or something like that?
Well, that's one way to see that you need classically that you need something like n log n examples. It's really, if you sort of cut through the notation, it really just is the coupon collector problem. And the thing is that forcing the learner to be proper in this case forces it to really completely identify the set S.
But what do you do in the case like epsilon is 1/3, and then how can you learn it with very few samples? It's kind of.
I think in that case you would just output the all ones function. So notice that all these functions in this concept class, they're very close to the all ones function. It is of course possible that your distribution E puts an enormous amount of weight on the one X where Fs is not equal to 1, but this you would see from a small number of samples.
Sorry, I don't understand. Like, wouldn't it be an improper learner if you output the all ones function? That's the whole issue, that it's not proper, isn't it, the issue?
Exactly. So the difference between proper and improper learning asymptotically only shows up if you set your epsilon to be very small. Right, so the fundamental theorem says that an improper learner, for an improper learner, the C dimension over epsilon example suffices. The lower bound you get from classical coupon collector is that for this concept class, so remember VC dimension is just 1 for this concept class, but the number of examples you need for proper learning is log 1 over epsilon. So it's bigger than what you need for improper learning by a log factor. And this log factor only becomes asymptotically significant for small epsilon.
Okay, like one last try. I just like, no, my question is that you say that if I set epsilon to say, I don't know, 1/10, 1/3, whatever, then one possibility is to output the all ones function. But I thought that the all ones function is not a proper output regardless of the precision epsilon set.
Yeah, so if you want proper learning, then you need log 1 over epsilon times 1 over epsilon, many examples. Let me just switch on the light here, it's getting dark. Maybe we should discuss this after the talk, give other people a chance to ask something.
Yeah, let's see if there's other questions, and then I can also stop the recording and you guys can continue chatting.
Should I look at the chat, or are you gonna?
No, it's fine. It's fine. It's fine. Oh, okay. So Anurag is asking if there's a similar theorem for proper learning.
Similar theorem.
As your fundamental theorem.
It's a good question. So you can certainly do proper learning with, so if you replace the log 1 over epsilon by log n, you can do proper learning for every concept class. And this follows from, so there's this nice there's this sort of core lemma called Sauer's lemma in pack learning. And Sauer's lemma says that if your concept class is on, okay, so I'm going to confuse n and m here. If I stick to the notation of this slide, then Sauer's lemma says that if you have a concept class of VC dimension D, then the number of this upper bounds the number of possible concepts in your concept class by something like log n to the power d. And you can now just do proper learning as follows. You keep your class C. This is the class of target functions, and a proper learner should find its hypothesis in that class eventually. And you just sample and sample and sample, and every new example that you get has an epsilon probability of eliminating every function from C, which is more than epsilon away from the target. So every new example that you get, it kind of eliminates I guess a 1 minus epsilon fraction of C. And now you just keep going, you keep getting new samples, you keep removing from C all the functions that are inconsistent with the examples that you've seen. And the total number of examples that you need now is going to only depend on epsilon and the size of the concept class. And this size of the concept class you can upper bound in terms of the VC dimension using the Sauer's lemma. So a general upper bound for proper learning is VC dimension times log of n, in this notation for n, divided by epsilon. And in this example, it just happens to be the case that log 1 over epsilon is the same as log n.
Okay, Anurag says, thanks.
Okay.
Maybe let me ask my question. I think it's an easy question. So I was just wondering if you, it's just a calculation, but I couldn't do it in my head. If you ask for what's the best way to encode all sets of a certain size into a quantum state that, and let's say you fix the number of qubits to be log n, and how many samples would you need to recover the set? You know, instead of just forcing it to be this superposition, just allow.
Yeah, I see. You want to use some sort of simple Holevo bound, lower bound, Holevo-based lower bound on the number of copies. Is that what you're?
I was asking for an upper bound. Yeah. Like, for example, if you use fingerprinting, or I don't know what's the best way to do this. Just some packing argument.
Yeah, fingerprinting is not going to work in this case, of course, because the different states ket S and ket S prime, they can be extremely close if they differ in just one point.
No, but my starting point is the set S, and I want to encode S into some state psi S, that when I'm given many copies of psi S, I can recover S. Oh, psi S doesn't need to be ket S; it could be something else.
I see.
It needs to be the same number of qubits.
You have n choose k possible sets.
Right.
I see. So you're just asking, like, what is the dimension needed if you have n choose k possible vectors that are pairwise almost orthogonal?
Yeah, except I wanted to fix the dimension and ask how many copies.
So in dimension,
and it's also not just almost orthogonal, I think, because it's not that I want to distinguish pairs, but I want to recover S.
So what does recover mean in this case?
No, recover S. So identify the state.
Oh, I see. In that case, the number of qubits should be something like k times log n, right? Because you're getting that many bits of information by recovering the set S.
Right, probably the lower bound, the information theoretic lower bound is tight. But in that, I was asking.
That's worse than what you get from our Johnson scheme lower bound. I think we're talking at cross purposes here.
Well, I wanted to fix the dimension of each state to be log n. So in your talk, the dimension of each ket S is, sorry, the number of qubits is log n, right?
Right.
And the question is how many copies of it. So I wanted to ask the same question and also fixing the state to have log n qubits, asking if there's a better state than ket S that allows you to recover S.
Let's see. So in our case, so you need. So let's consider the situation where quantum coupon collector requires the same number of samples as classical. So let's say that k, or let's say that m, the number of missing items, is polynomial in n.
Yeah.
So then our lower bound says that you need something like n log n copies of the state, and each copy of the state is itself log n qubits. So the number of qubits you need to be given is something like n times log n squared. This, of course, is information theoretically terrible, because if I want to encode one out of the n choose k possible sets, k times log n bits, just classical bits would suffice. And
yeah, if k is n over 2, it's not that far, right?
Well, it's a log factor apart.
But that information theoretic lower bound allows me to encode states into non-product states. I wanted to ask you of groups of.
Yeah, so yeah, one way to do it would just be to kind of, to just enumerate the elements of, actually that's not efficient. A better way to do it is just to give the incidence vector, the characteristic vector of the set S, using n classical bits. This, of course, is not a product state.
Yeah, right.
It's not a tensor product of copies of the same state. And I'm not sure what you're getting at with this question, so maybe I could give a better answer if you tell me where you're going with this.
Okay, let me tell you. I'll take it off. Or take any other questions. Take it offline, and then I can ask you more precisely.
Mm-hmm.
So are there? So then I can release everyone. Are there other questions? Okay, if there's no other questions, let me thank Ronald on behalf of the audience for his seminar. Let me also announce that next week at the same time, we'll have a talk by Yuan Su from UMD, and he's going to tell us about his work with Andrew Childs, Min Tran, Nathan Weeb, and Shuchen Zhu on a theory of Trotter error. And that seminar next week might be the last seminar of the program, because the week after that, we'll have a workshop. We might have a seminar the week after. Okay, so thanks everyone. Thanks Ronald, and I'll stop.
Thanks everybody.